Okay, welcome everybody to the first Supert seminar talk this semester, and we are very happy to have Paolo Aluffi speaking about the Grothendieck class of the moduli space appointed stable curves of genus 0. Please go ahead.
Okay, thank you. Thanks for the invitation. It's an honor, and I've known about your seminar for a long time, but I've not seen many of your talks, but I should, and they are recorded somewhere, right? So they're accessible. So this is my plan, and it's probably a little over-ambitious, let's see, the key point here will be a computation of the class in the Grothendieck ring, which is the same information as the Betti numbers for this particular space. And I chose this topic after talking to Leonardo, and I apologize with Leonardo and maybe others in the audience that you may have seen something like this already in the past. I talked about this now for a little while. But it seemed a nice topic also in pedagogical terms, so to speak. And the talk is not so much about my result as an excuse or an opportunity to advertise M0 and bar, which is a beautiful space that everybody should be familiar with. And this is joint work with Matilde Marcolli here at Caltech, Stephanie Chen, who used to be a student at Caltech and now is a graduate student at Harvard, and Eduardo Nascimento, who's still an undergraduate here at Caltech. So there's two papers. The one with Chen and Marcolli is about the log concavity, and I hope to have some time to say something about it. And the second one with Eduardo and Matilde Marcolli is on this very new journal that deals with moduli spaces, moduli. Let's see. So M0 n bar will be the moduli space of stable n-pointed genus 0 curve. And the theorem, I can just put it on the board, it's this, that the class in the Grothendieck group of M0 n bar is this particular combination. And little s and capital S, these are Stirling numbers. I will remind you of what those are. So this is a very explicit, totally explicit formula for the Grothendieck class of M0 n bar. I will also tell you what I mean by Grothendieck class, and actually I will phrase this in terms of Betti numbers very, very soon. First and second kind. These are very simple combinatorial objects that everybody should know about, but honestly I don't deal with Stirling numbers all the time. I'm more familiar with binomial coefficients, but it's the same kind of combinatorial things. Now, M0 n bar is a smooth projective variety, dimension n-3. M03 bar is a point. It stands for the only way you can place 3 points on a projective line up to isomorphism. M04 bar is P1, and so on. I'll try to give a sense for the construction of M0 n bar in general. And what the theorem tells you is this, that for n between 3 and whatever, you can write down the Grothendieck class. There's this pleasant Christmas tree kind of picture. It needs to be symmetric because this is a smooth projective variety, and this information, the numbers you're seeing, are just the Betti numbers of the variety. So the coefficient of L to power L in the Grothendieck class of M0 n bar is nothing but the 2Lth Betti number of M0 n bar. This fat L stands for the Lefschetz state motive, is just the class in the Grothendieck group of varieties of the affine line. So if you want to extract the individual coefficients, that is the Betti numbers, this is it. This comes out of the main formula. It's an explicit, completely explicit formula. So what can I say intelligent? There's nothing particularly intelligent here, but if L is too large, of course, this has to be 0, and that's a combinatorial identity of Stirling numbers which I've not seen anywhere else. I asked Don Zagier, and he didn't seem to find it very remarkable, but it tells you that if you multiply Stirling numbers in a certain way, then you will get 0 for L large enough. It is well known that the odd cohomology of M0 n bar is equal to 0. Yeah, there you go. This formula must be 0 for L larger than n-3. This is not combinatorially obvious as far as I can tell. Also clear from geometry, but not obvious, the symmetry that you saw in the picture on the previous page. Let me challenge you to prove that symmetry just based on this combinatorial formula. It's mysterious, at least to me. So about Stirling numbers, there's two kinds of Stirling numbers, first kind and second kind. The definition is just this. Now, you consider the polynomial x times x minus 1 dot x minus n plus 1. This is called the falling factorial for clear reasons. And then the two kinds of Stirling numbers are just coefficients in the change of basis with the ordinary monomials. So if x parenthesis sub n is the falling factorial, then the coefficient of that expansion will be the Stirling numbers of the first kind, and if you reverse that connection, that matrix, you will get second kind. Here's an example. The falling factorial for x over the 3 is x times x minus 1 times x minus 2, so we are able to expand that, and the coefficients are, as you can see. So the S33 must be 1, S32 must be negative 3, and S31 must be 2. This is a nice exercise, actually. For whatever reason, the Stirling numbers of first kind are more mysterious than the Stirling number of second kind. For the second kind, you can write a nice formula. It's a nice exercise from the definition. There is an analogous formula, I mean, using binomial coefficients and being a little clever for Stirling numbers of the first kind, but it's somehow more difficult to obtain. There's a matrix form of the result which I like, so let me put it on the slides. This is, I'm collecting the Stirling numbers of the first kind on the left and of the second kind on the right. And it just so happens that by definition, the product of these two matrices must be the identity, just because they are change of basis, as I pointed out in the previous slide. So I'll use this notation. If I put increasing powers of q, whatever q may be, on the diagonal of an infinite matrix, I'll call that 1 sub q, so 1 sub 1 is the identity. And I also need this peculiar notion of kth trace. The kth trace is the sum of the entries in the kth subdiagonal. So the ordinary trace is trace 0. Then I can do this. I mean, I pointed out that just by definition, this is immediate from the definition, the first kind of matrix times the second kind of matrix must give me the 1, 1, the identity matrix, infinite identity matrix. Now, you cannot stop me from putting some identities in between the two Stirling matrices. And then what I'm going to do is interpret those as this kind of matrices, and then put a q instead of 1. Actually, q will be L.
There is a question from Alan on the chat. He's asking whether the Stirling numbers of the first kind are of predictable sign based on the distance from the diagonal.
Come again, R?
Of predictable sign based on the distance from the diagonal.
The answer is certainly yes, although I'm not the one who does the prediction, but these numbers are, yeah. I believe that is the case, and there are many books written on Stirling numbers. I'm sure that this is a fact that should be easy to locate. Yeah. Or maybe it is even clear just from the definition. Who knows? Maybe not. If Alan says it's not clear, then it's not clear. But there we go. So I take this observation and deform it by putting an L and an L inverse on the diagonal in these matrices in between, and this is what I get. This is a computation. So, for example, the first trace, which is highlighted in red, if you can see colors, of this matrix is this: 1 minus L plus 3L minus L, 3L squared plus 6L squared minus 6L cubed. These are just those diagonal entries. And if you add them up, you get a predictable object, and then you can maybe write this: 1 minus L to the second power times the first trace of this matrix is 1, and 1 happens to be the class of M03 bar. So to rephrase the main theorem, this is it. So if you change 3 into n, you get a true statement. The class of M0n bar promise is 1 minus L to the n minus 1 times the n minus second trace of this particular matrix that I had on the board. It's still up there. Okay. So I find this very pleasant, but I don't know, just another way to package the statement of the theorem. Questions? Other questions? No, I don't see the chat indication, so Leonardo will have to tell me if anybody asks a question. So I want to go through the construction of M0 bar, or at least give some sense for the construction of M0 bar. It's a stupendously pleasant object. Goes back to Knudsen, I believe, was the first to define it, to construct it back in '93. Then it was understood in several different ways. Sean Keel, in his PhD thesis at Chicago with Fulton, gives an alternative construction in '92, and that construction gives a determination of the cohomology / Chow ring. So Keel's result, yeah, it's the Lth Chow component of the Chow ring is isomorphic to a true Lth homology. There's no odd cohomology, and there's a recursion for the rank of H2L. So here it is. Now if you let AKN be the rank of H2K, so 2kth Betti number, then AK3 is 1 if K is 0 and 0 otherwise, and otherwise you have this complicated looking recursion that allows you to determine all the Betti numbers recursively. Right? So the numbers you saw 5 slides ago satisfy this recursion. There are other proofs of this recursion. There's one in Fulton McPherson's paper on the annals. Getzler has one, and then I'm putting money in red because this is the one that I will lean on for the rest of the talk. In '95, put together a generating function with the Poincaré polynomial, so the Betti numbers, and then the statement is that this generating function satisfies a differential equation and a functional equation, and the Poincaré polynomial is what you get by replacing t squared with L. The odd powers of t correspond to the odd cohomology, so they are not there. And so just to restate the same thing, I can state it like this: if M is 1 plus Z plus this sum of the class of M0 and bar in the Grothendieck group of varieties, Zn minus 1 divided by n minus 1 factorial, then there you go. There's a differential equation and a functional equation. They are all very simple. This is stated by Manin in this paper back from 1995, and in terms of the Grothendieck class, it's also can be found in a paper by Manin and Matilde from 2006.
What does m to the L mean?
M to the L, you can write it as the exponential of L times the logarithm of M. No. So by having cleverly chosen M to start with 1, you can make sense of the logarithm of this series. Then you can multiply that by L and take the exponential. Again, that makes sense, and that gives you something that you could write as a power series, and the claim is that that's the same as this, the same as L square M plus 1 minus L times 1 plus Z plus 1L. Yeah, so M to the L excellent question stands for the exponential of L times the logarithm of M. Okay, so what we did was solve these equations. Somehow they were around for 30 years, but I did not find a solution anywhere. The reason maybe is that once you have the recursion, you have all the information you want. If you want to compute this for n equals 100, the Maple will take a fraction of a second to do that. Nevertheless, it seemed worth trying to understand the structure of this generating function more deeply, so to just write it as in a more explicit form. And this is the more explicit form. It's not the most beautiful formula I've ever seen. In fact, it's 2 formulas, but it is very explicit. Now, I'm not going to attempt reading this, but there's the same problem that Leonardo mentioned. There's a funny exponential, so this really means the exponential of this whole, so the exponential of this exponent times the logarithm of this of the base. Okay, so other than being somewhat unpleasant, it is a very explicit formula. In fact, the second formula implies the Stirling expression that I put on the board, which is more pleasant, but that's what it comes from. So if you just do a little bit of work and write out what the coefficients are, you find that formula in terms of Stirling numbers that I put earlier. Why do I put the first form? Because the first is what I find first, and then it implies the second, and it's also independently useful. Okay, time for questions, comments. I should keep an eye on the time. I'm extremely bad at managing my time.
Yeah, question. Is there some obvious reason in advance that the motive is going to be a polynomial in L?
How far in advance? I mean,
like if I had a circle action with isolated fixed points, I would know that, but I guess I don't have
right,
that here.
Right. I think probably the best source for that is Manning-Marcoli. Yeah, so it's mixed state, people like to say, but this paper that you can find, the title has to do with F1, and in there's a good explanation of that, I think. Do I have a better answer right now? Not on the top of my head.
Like a cell decomposition would be, of course, the...
Right, but that's tricky. The cell decomposition isn't there. I mean, that's what Manning and Marcoli discuss in their paper. It behaves as if it had cell decomposition, even if it doesn't really on the nose, I think. There are subtleties that need to be taken care of. I'm saying this, I hope I'm not missing right now some memory of some easier thing I could say, but yeah, anyway, it happens to be a polynomial in L. I mean, to some extent, once you know that, once you know Sean Keel's, right, that this is just reading off the Poincaré polynomial, then it is the Poincaré polynomial, so it needs to be a polynomial in L, but you want a priori reason why it should be, and then I'll send it to Manning-Marcoli. I think so. I don't know whether that's a good answer or not. But. Okay, so the plan for the talk is to say more about M0 and bar, then to talk about the recursion at the level of Grothendieck classes. And then I never do this in talks, I never give proofs. I don't believe really that one can be effective in giving a proof in a talk, but this is an exception because after the fact, once you know what the formula is, then you can find reasons that get you to the formula quickly, and I'll try to do that. And then if I have time, I'll give one consequence and some contextual comments for of the result. So I'm mindful that there should be students in the audience, so I'll say words that I think might be useful to them. M0n is a modular space, and that's a luxury we have in algebraic geometry to be able to use algebraic geometry space to parameterize algebraic geometry spaces. So, for example, projective space itself, or the Grassmannian, is a modular space for simple-minded objects, one-dimensional subspaces for projective space, or subspaces of arbitrary dimension for Grassmannian. Mg is a very famous object that parameterizes isomorphism classes of genus G curves. And to be a modular space is not just satisfying the requirement of parameterizing something. There's more to it. For example, for the Grassmannian, you have a universal subbundle. You have a bundle over the Grassmannian, which realizes what the Grassmannian is there for. So the fiber over a point of the Grassmannian is the corresponding subspace. And the same happens for curves. You have a universal curve mapping to Mg, the inverse image of the isomorphism class of C is the curve C. And Cg is itself a modular space. You can realize it as Mg, where you are parameterizing the curves C along with a point P, so that's called Mg1. Parameterizes genus G curves along with a point chosen on the curve. So this map from Cg to Mg simply forgets the extra point. Now you can iterate this and get Mgn, genus G curves, along with n distinct points, and you have a universal pointed curve, which is nothing but the next step in the sequence. So again, you have this map from Mgn plus 1 to Mgn, which forgets the last point. Now G is the simplest case. That's a case in which these are actually schemes rather than stacks or more complicated objects. For genus 0, we are just looking at smooth genus 0 curves, and the genus 0 curve is P1. So we're just looking at P1 and trying to put n distinct points on P1, and in this business they are ordered points. After all, you must know which the last one is, right? So M0n stands for P1 along with the choice of n points on P1. Now, this is the topological picture, right? P1 is a sphere, but we are just extracting the combinatorics, and then this is maybe better picture, is just a line with n distinct points. Up to isomorphism, you want to do this up to isomorphism, and for P1 this means up to a Möbius transformation. So you can fix the first 3 points to be 0, 1, and infinity, 0, 1, 1, 1, and 1, 0. And that's what you're parameterizing. Now, I'm going to ignore what this may be for less than 3 points. For 3 points, you have fixed those 3 points, so there's only one way to do it. That means M03 is just a point. M04 is a little more interesting. You have fixed the 3 points, 0, 1, and infinity. The 4th point can travel happily on P1, except that it cannot collide with 0, 1, or infinity. So, well, this means that M04 can be realized as P1 itself minus the 3 fixed points, 0, 1, and infinity. What about M05? Well, you can take 2 copies of P1 and then remove 0, 1, infinity from both copies, and also remove the diagonal because you don't want the new point to be equal to one of the old points. And so on and so forth. You can write this M06 as a product of M04s, P1s minus 3 points, minus diagonal. And in general, M0n is a certain n minus 3-dimensional smooth variety, which is just the complement of the diagonals in M04, which is P1 minus 3 points to the n minus 3rd power. So there's a problem. No, this is not compact. You're not allowing the points to come together, and this is unpleasant. You want to have compact spaces. Intersection theorem works much better on compact varieties, and so on. Is there a modular compactification? Now, if you view this as the complement of the diagonals in what looks like a perfectly nice variety, you might think of compactifying that variety. And that doesn't quite work. I mean, for M04, it still works. M04 bar, no, there's no other choice. M04 without the bar is P1 minus 3 points. If we want to compactify that, the only way to do it is P1 itself. For M05, it's already interesting. The easy compactification, that is M04 cross M04, compactify both factors, is P1 cross P1. It just so happens that this cannot be viewed as a modular space of point configurations. And what that means is that the limits, as the points come together, depend on the choice of which points are identified with 0, 1, and infinity. Now, if we had more time and I remembered how to do it, I could show it. It's a very simple computation. So somehow you have to throw away this compactification. And, of course, the situation gets worse as you increase n. Now, the amazing fact that Knudsen proved is that for all n, there exists a modular compactification. And, in fact, this modular compactification has a beautiful description. As we try to illustrate, each point of the compactification of M0n may be viewed as a configuration of points on a tree of P1s. Now, there will be a more precise statement below. And then we have morphisms are, as we expect, that forget the last point and that realize the source here as the universal curve for the target. So the picture to keep in mind is the following. You let 2 points come together. The P and Q are traveling and they want to hit head-on to each other. And as they do that, then in the limit, you sprout a new component P1 where the collision happens and place P and Q as distinct points on this component. So the movie I have in mind is these 2 points coming together, and then as they reach each other, they miss and they deposit themselves on this extra P1 that has conveniently appeared for them. Now, the new component has 3 special points, right? The intersection with the old component and P and Q. And that means that up to isomorphism, you cannot move P and Q anymore. P and Q are rigid there. They cannot go anywhere. So once they land where they are, that's it. Which is promising. I mean, this means that the limit exists and there's no further motion that can happen over there. So MZ4 bar should be viewed as follows. You have P4 moving away from 0, 1, and infinity. That's the M04 part of the story. And then maybe P4 collides with P1, and P1 was the point 0 that we called 0, or maybe it collides with P2, that's 1, or with P3, that's infinity. In each of these cases, a new P1 has sprouted, and the points P1 and P4, P2 and P4, P3 and P4 land on this extra component. And again, the situation is rigid now. Each component has 3 special points, so now the automorphisms are taken care of. Now, what if 3 points come together? Well, the component will sprout conveniently, but then the 3 points will land onto the new component, and now this component has 4 points. By the way, I have a cursor here. I don't know if you see it. Every now and then I use it to point at something that's not maybe the best possible way, but
we see it. Yes, we see it.
You saw it? That's good. You see it. So in this component I have 4 points, which means, well, it reminds me of M04, and that was a one-dimensional object, and there was some moving that could happen, and now P4 and P5 could come together, or P3 and P4 could. So in that case, it would sprout yet another P1. So somehow you keep the sprouting until you reach a position in which your situation is rigidified. Okay, so that takes care of somehow the intuition here. The point of M0 and bar are trees of P1s with n marked point, such that each component has at least 3 special points. Those components that have exactly 3 special points are done for. You cannot do anything with them. In the others, you can still move. So that's what a stable n-pointed genus 0 curve is. That I think is my title. So here's a point of M0 and bar. If I've done my job correctly, then every component has at least 3 special points. For example, this component over here has 4 special points. This has 4 special points. This pool component only has 3 points. This has 3 points. This has 3 points. So, okay, now this is just combinatorial information, and in fact, that information can be written better. There's a better way to express the same information, and I'll attempt to do that in the next slide. So you put you consider a graph again, and there will be one internal vertex for each component of the whole graph, and you will have edges joining vertices if the corresponding components meet, and the marked points are drawn as leaves in this diagram. So for the example I had on the previous slide, this is what you would get. It's a dual tree, right? So the vertices you see over here corresponds to the component, I hope. Let's see, I have 1, 2, 3, 4, 5 components, and I have 1, 2, 3, 4, 5 vertices. These are the leaves corresponding to the 3 points P7, P8, and P9, and so on. There's 2 leaves on this component because there's this P6 and P1, those are the marked points, etc. Okay, so you get these dual trees, and as we will see in a moment, it's a better way to view the combinatorics here. So M0 and bar has a stratification. The strata correspond to these stable trees. These are the trees I get from, as in the previous page, with n leaves. Now, the dual tree of points on M0n are just one component with n leaves, numbered leaves, of course. That's the largest stratum in M0 and bar. It's just M0n. The dimension is n-3, as we know. From this point of view, this is the picture I should draw for M04 bar. The first picture is for M04, and these 3 pictures correspond to the 3 points that I have to add to M04 to get P1, and they are just the dual pictures of what I drew a few slides before. Do I have any clever comment here? Right, so the stability corresponds to the fact that you have at least valence 3 at each vertex. Right, that's the statement corresponding to requiring 3 special points on each component in the other picture. There you go. So if you start with 4 leaves, you enumerate all possible ways you can draw trees with valence at least 3, and these are all the pictures you get.
That's another point. A question in the chat.
Thank you.
Moria Elkin asks, in the original tree picture, are marked points allowed to collide with the intersection points?
So in this picture, can I have P1 run on the intersection point? If it tries to do that, there will be another P1 sprouting taking care of that. So the two components will separate and P1 will go in the middle, so to speak. So in a sense, no. If you try to do that, then you will have to specialize further. I hope that answered the question. I was going to try to do this for M05. It becomes already a fairly large picture, but you see it's a combinatorial game, right? You just have to find all trees with a certain property, and I promise that once you label the leaves, you will have 10, this is supposed to be 10 leaves, have trees like this, and 15 trees like that, and I claim that this, the big component, of course, has dimension n-3, that's true in this case. This component will, these 10 components will have dimension 1, 10 strata, I should say, will have dimension 1, and these are 15 zero-dimensional strata. Why do I know the dimension? Because of something magical, that all these strata are in fact products of M0i's. This is the way it works. You can start with this. This is still my running example, and you just separate in the middle every edge, and what you're left with is a bunch of trees with just one component, which, as we know, correspond to M0i. So this is a copy of M03, this is a copy of M03, this is a copy of M03, this is M04, and this is also M04. I think I mapped them here. There we go. So I can use this to count dimension. These are, the claim is that then this particular guy will have dimension 2, because it's a product of a point, P1 minus 3 points, P1 minus 3 points. There you go. Dimension 2. So you can easily evaluate the dimension given one of these pictures.
Paolo, just one more question. So Moraya just wants a clarification. So there cannot be any triple intersections, right?
There cannot be any triple intersection. Where?
So in the original, I think it was in the original tree realization of M0n. It's not in the dual picture. Yeah.
Right, there's no triple intersection. Yeah, these are nodal curves in the mildest possible sense of the term. Okay, probably it would be almost time to take a small break, but let me see if I can get to the construction of M0n to finish this discussion. Now M0n bar. Sorry, M0 n plus 1 bar is the universal curve of M0 n bar. So, and I know that this map has to forget Pn plus 1. So, to stick to an example, let's look at M05 bar that maps to M04 bar by forgetting P5, and we should understand the fibers. The fibers should look like this, right? If P4 is not 0, 1, or infinity, then this is what you should get. If P4 had collided P1, then the corresponding curve, that is the fiber of this map, should look like this. How to do that? Well, you start with the simplest possible, the wrong compactification, P1 cross P1, with this nice configuration of 0, 1, infinity, P1, P2, P3, and P4. P4 is the diagonal. If you are at this point down here, then your fiber looks exactly what it should look like. Now, P4 is some point other than P1, P2, and P3, and what I get is just this picture. Trouble arises when I'm at the intersection of the diagonal with these sections, because that corresponds to P4 hitting P1. Well, as algebraic geometers will see, that there's something you could do. You could blow up those blue points, and then you will achieve exactly the sprouting that I was advertising a moment ago. The sprout is, the new P1 is just the exceptional divisor. And if you're familiar with blowing up a surface at a point, you will see that the section corresponding to P1 will miss the diagonal, right? And will hit the exceptional divisor at some point, which is not the same point that the diagonal, the property transform of the diagonal hits it. So what you get, now I hope you see the red picture you get if you blow up, is exactly the picture you expected to get. This is the picture you should get. There we go. So in fact, M05 bar is the blow up at 3 points of M04 bar cross P1. So what Sean proved is that this works in general. In general, M0 and plus 1 bar is the result of a sequence of blow-ups along smooth subvarieties of codimension 2. All the centers are products of previous moduli spaces. The general point and center looks like this. It's the simplest kind of nodal curve, and I of the points are on one component, j on the points are on the other component. And this is what you can use to prove the recursion for the Grothendieck class. Yeah, I've not said yet what the Grothendieck business is, but I was referring to the Grothendieck group of varieties, which is what looks like a simple-minded object and turns out to be an extremely deep and profound object. But you just take a free abelian group on isomorphism classes and mod out by these scissor relations. If y is x minus z, then you pretend that x is the sum of y and z. If you take product, that gives you a ring structure. L, that has appeared many times so far, is the class of A1. So, little exercise if you've not done it before. Pn can be written as 1 plus L plus dots plus Ln, and that is this pleasant rational function. Now, the Grothendieck group is universal with respect to all invariants which satisfy the scissor relation. That's what free abelian groups modular relations are there for. And the fact that I stated earlier was that the class of M0 and bar in this group, in this ring, is this particular sum. It's coefficients coming from Betti numbers times L to the k. This strictly has to do with the vanishing of the outcome homology. So since I know how to construct M05 bar as a blow up, I can do this. And if I take P1 cross P1, I blow it up at 3 points, that I take those 3 points away and replace them with 3 exceptional divisors, then I get this formula. So you are now able to compute the Grothendieck class of M0 and bar by this operation. So this is the third line in my picture I had at the beginning. So you do the same in general. In general, it's a simple game. If you take a blow up, you are taking B away and replacing it with a projective bundle over B. If everything is smooth, and that's what you get. You have a level of Grothendieck classes. So at least you should believe that this can be done. M0 and bar is obtained from the previous one by crossing by P1. L plus 1 is the class of P1, and then doing some blow-ups, which amounts to which is taken care of by this summation. So if you do some bookkeeping, this is what you get. This is the same recursion I put on the slides way at the beginning about the Betti numbers. So you can practice doing this for M05 bar, and this will work. All right, so I think this is a good time to take a 5-minute break, although we are a little past the half point. Anybody wants to chip in?
Thank you very much. Yeah, very nice story.